Your approach to estimating the power factor using the neutral current is valid in certain scenarios, though it's essential to understand its limitations and assumptions. The power factor represents the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. It indicates how effectively electrical power is being used. A power factor of 1.0, or unity, signifies that all the power supplied is being used for useful work, while a lower power factor indicates that a portion of the power is being wasted. In a balanced three-phase system, the neutral current should ideally be zero. However, in real-world scenarios, imbalances in phase loads and harmonic currents can cause a non-zero neutral current. The formula used, involving the square root of the sum of squares of phase currents minus their cross products, is indeed a way to calculate the theoretical neutral current in an unbalanced three-phase system, assuming only fundamental frequency components are present. The difference between the calculated and actual neutral currents, NDIF, provides an indication of the magnitude of harmonic currents and other factors contributing to the imbalance. The subsequent formula, 1 minus NDIF divided by the sum of phase currents, provides an estimate of the power factor. However, it's a simplified approximation and may not be accurate in all situations. There are several factors to consider. Firstly, harmonic currents significantly impact the neutral current and power factor. Harmonics are multiples of the fundamental frequency, typically 60 Hz in North America. Nonlinear loads, such as electronic devices, variable frequency drives, and some types of lighting, generate harmonic currents. These currents don't cancel out in the neutral conductor like fundamental frequency currents in a balanced system, leading to a higher neutral current. Your calculation doesn't explicitly account for harmonics, which can skew the results. To accurately determine the power factor in the presence of harmonics, specialized equipment like power quality analyzers is needed. These analyzers measure the true root mean square current and voltage, as well as the harmonic content, allowing for a precise calculation of the true power factor. Secondly, the voltage waveform is assumed to be sinusoidal in your calculation. However, voltage distortion can also occur, especially in systems with significant harmonic currents. Voltage distortion affects the apparent power calculation and consequently the power factor. Power quality analyzers can measure voltage harmonics and provide a more accurate assessment of the power factor under non-sinusoidal conditions. Thirdly, the accuracy of your current measurements is crucial. Errors in the current readings will directly affect the calculated neutral current and power factor. Ensure that you are using calibrated and accurate current clamps or meters. Furthermore, the placement of the current clamps is important to capture all the current flowing in each phase in the neutral conductor. Fourthly, the formula you use for the calculated neutral current assumes a purely sinusoidal waveform and balanced system conditions, which are rarely perfectly met in practice. In reality, there will always be some degree of imbalance and harmonic distortion. While your simplified approach can provide a reasonable estimate under certain conditions, it's important to recognize its limitations and potential inaccuracies. A more accurate method for determining the power factor involves directly measuring the real power, apparent power, and reactive power using a power quality analyzer. The power quality analyzer calculates the true power factor based on these measurements, taking into account harmonics, voltage distortion, and imbalances. Fifthly, calculating the apparent power using the formula involving the square root of 3 voltage and neutral current is not entirely accurate for power factor determination. This calculation might be relevant for size in the neutral conductor, but it doesn't directly translate to power factor. The correct apparent power calculation should use phase currents and voltages. For a three-phase system, the apparent power is the square root of 3 multiplied by the line voltage and the line current. The reactive power, which contributes to a poor power factor, is related to the phase angle between the voltage and current waveforms. To improve the power factor correction techniques are employed. These techniques typically involve adding capacitors to the electrical system to compensate for the reactive power. By reducing the reactive power, the apparent power is minimized and the power factor is improved. Power factor correction can lead to several benefits, including reduced energy costs, increased system capacity, and improved voltage regulation. To reiterate, while your approach can offer a quick estimate of the power factor based on neutral current, it's essential to understand its limitations and potential inaccuracies, especially in systems with significant harmonic distortion or voltage imbalances. A comprehensive power quality analysis using specialized equipment provides a more accurate assessment of the power factor and helps identify the underlying causes of poor power factor. In your provided example, you have phase currents of 54 amps, 43 amps, and 58 amps, with a measured neutral current of 25 amps. Your calculated neutral current is 13.45 amps, resulting in a difference of 11.55 amps. Based on your formula, you arrived at a power factor of 0.92. While this value might be in the ballpark, it's crucial to consider the factors discussed earlier, such as harmonics and voltage distortion, before drawing definitive conclusions. To accurately determine the power factor, it's recommended to use a power quality analyzer to measure the real power, apparent power, reactive power, voltage harmonics, and current harmonics. This will provide a comprehensive understanding of the power system's performance and allow for appropriate power factor correction measures to be implemented if necessary. Remember that maintaining a good power factor is essential for efficient energy utilization and reliable operation of electrical equipment. Poor power factor can lead to increased energy costs, voltage drops, and equipment overheating. Regular power quality monitoring and power factor correction are crucial for optimizing the performance of electrical systems. To put it in a different way, estimating the power factor by looking at the neutral current, especially as a ratio of the phase currents, can work directionally, but is hardly ever used by professional engineers in practice because it is fraught with error and inaccuracies. Firstly, the method assumes a linear system. A linear electrical system means that the loads connected to the circuit behave in a predictable manner, where the current is directly proportional to the voltage, following Ohm's law. In simpler terms, the impedance of the loads remains constant regardless of the voltage or current changes. However, many modern electrical systems contain nonlinear loads such as electronic devices, computers, and LED lighting. These loads draw current in a non-sinusoidal manner, creating harmonics in the current waveform. The presence of harmonics violates the assumption of linearity and can significantly affect the accuracy of power factor calculations based on neutral current measurements. Secondly, it assumes there is no harmonic currents. Harmonic currents are multiples of the fundamental frequency current, which is typically 50 Hz or 60 Hz, depending on the region. These harmonics are generated by nonlinear loads and can cause distortion in the current waveform. The presence of harmonic currents can significantly increase the neutral current even in a balanced system. As a result, using the neutral current to estimate the power factor without accounting for harmonic currents can lead to inaccurate results. Specialized equipment, such as harmonic analyzers or power quality meters, is needed to measure and analyze harmonic currents accurately. Thirdly, the method is highly sensitive to imbalances in phase currents. In a perfectly balanced three-phase system, the phase currents are equal in magnitude and 120 degrees apart. However, in reality, phase currents are often unbalanced due to unequal loading or variations in the impedance of the phases. This imbalance can cause a significant increase in the neutral current, even if the power factor is close to unity. As a result, using the neutral current to estimate the power factor can be unreliable in unbalanced systems. To accurately assess the power factor in unbalanced systems, it is necessary to measure the voltage and current in each phase separately and calculate the power factor for each phase. Fourthly, the method does not account for displacement power factor versus true power factor. The displacement power factor, also known as the fundamental power factor, is the cosine of the angle between the fundamental voltage and current waveforms. It only considers the phase shift between the voltage and current at the fundamental frequency. However, the true power factor takes into account both the phase shift and the distortion caused by harmonic currents. The true power factor is defined as the ratio of the real power to the apparent power. In the presence of harmonic currents, the true power factor is always less than the displacement power factor. Therefore, using the neutral current to estimate the power factor without considering harmonic distortion can lead to an overestimation of the power factor. Fifthly, it is susceptible to measurement errors. Measuring the neutral current accurately can be challenging, especially in systems with high harmonic distortion or unbalanced loads. Current transformers, which are commonly used to measure currents in power systems, can be affected by harmonic currents and may not provide accurate readings. Furthermore, the placement of the current transformer is critical to ensure that it captures all the neutral current. Any errors in the measurement of the neutral current will directly affect the accuracy of the power factor estimation. Sixthly, the relationship between neutral current and power factor is complex and nonlinear. There is no simple formula that can accurately relate the neutral current to the power factor in all situations. The relationship depends on various factors, such as the type and magnitude of harmonic currents, the degree of imbalance in phase currents, and the characteristics of the loads connected to the system. As a result, any attempt to estimate the power factor based solely on the neutral current is likely to be inaccurate and unreliable. Instead of relying on the neutral current to estimate the power factor, it is recommended to use specialized equipment such as power quality meters or harmonic analyzers to measure the power factor directly. These instruments use sophisticated algorithms to accurately calculate the true power factor, taking into account harmonic distortion, voltage imbalances, and other factors that can affect the power factor. Power quality meters typically measure various parameters such as voltage, current, real power, reactive power, apparent power, harmonic distortion, and voltage imbalances. These measurements can provide a comprehensive assessment of the power quality in the system and help identify potential problems such as low power factor, excessive harmonic distortion, or voltage imbalances. Based on these measurements, appropriate corrective actions can be taken to improve the power quality and reduce energy costs. In summary, while the neutral current can provide some indication of the power quality in a three-phase system, it is not a reliable indicator of the power factor. The relationship between neutral current and power factor is complex and nonlinear, and any attempt to estimate the power factor based solely on the neutral current is likely to be inaccurate and unreliable. To accurately measure the power factor, it is recommended to use specialized equipment such as power quality meters or harmonic analyzers. In practical terms, if you're tasked with improving power factor, focus on these key areas. Firstly, conduct a power quality survey. Use a power quality analyzer to measure voltage, current, power factor, harmonics, and imbalances over a period of time, typically at the main service entrance and at critical loads. Secondly, identify nonlinear loads. Determine the sources of harmonic currents by examining the types of equipment connected to the electrical system. Common culprits include variable frequency drives, electronic lighting ballasts, computers, and other electronic devices. Thirdly, consider harmonic filtering. Install harmonic filters to reduce harmonic currents and improve the power factor. Harmonic filters are designed to block specific harmonic frequencies and prevent them from propagating throughout the electrical system. Fourthly, implement power factor correction capacitors. Install power factor correction capacitors to compensate for the reactive power consumed by inductive loads. Capacitors provide leading reactive power, which counteracts the lagging reactive power of inductive loads, thereby improving the power factor. Fifthly, balance the loads. Distribute loads evenly across the three phases to minimize imbalances and reduce the neutral current. Uneven loading can lead to increased losses and voltage drops, as well as higher neutral current. Sixthly, use energy-efficient equipment. Replace old, inefficient equipment with energy-efficient alternatives that draw less reactive power and generate fewer harmonics. Energy-efficient equipment can significantly reduce energy consumption and improve the power factor. Seventhly, regularly monitor the power factor. Continuously monitor the power factor to ensure that it remains within acceptable limits. Power quality meters can provide real-time data on the power factor, allowing for prompt corrective actions if necessary. Eighthly, consult with a qualified electrical engineer. Seek the advice of a qualified electrical engineer to assess the power quality and recommend appropriate power factor correction solutions. An electrical engineer can perform a comprehensive analysis of the electrical system and design a customized power factor correction system to meet specific needs. Remember that power factor correction is an ongoing process that requires regular monitoring and maintenance. By implementing these measures, you can improve the power factor, reduce energy costs, and enhance the reliability and efficiency of the electrical system. Furthermore, understanding the nuances of power factor and its impact on electrical systems requires an understanding of the different types of power. Firstly, real power is the power that performs actual work in an electrical circuit. It is measured in watts, W, or kilowatts, kW. Real power is the power dissipated by resistive components in the circuit, such as heating elements, incandescent lamps, and resistors. Secondly, reactive power is the power that is stored and released by reactive components in the circuit, such as inductors and capacitors. It is measured in volt-amperes reactive, or VAR, or kilovolt-amperes reactive, kVAR. Reactive power does not perform any actual work, but it is necessary for the operation of inductive loads such as motors, transformers, and reactors. Thirdly, apparent power is the vector sum of real power and reactive power. It is measured in volt-amperes volt-amps, or kilovolt-amps kV-amps. Apparent power is the total power that is supplied to an electrical circuit, regardless of whether it performs useful work or not. The power factor is defined as the ratio of real power to apparent power. Power factor equals real power divided by apparent power. It is a dimensionless quantity that ranges from 0 to 1. A power factor of 1 indicates that all the power supplied to the circuit is being used for useful work, while a power factor of 0 indicates that all the power supplied to the circuit is being stored and released by reactive components. Inductive loads such as motors and transformers typically have lagging power factors, meaning that the current lags behind the voltage. Capacitive loads such as capacitors typically have leading power factors, meaning that the current leads the voltage. The power factor can be improved by adding capacitors to the electrical system to compensate for the reactive power consumed by inductive loads. By reducing the reactive power, the apparent power is minimized and the power factor is improved. A low power factor can have several negative consequences, including increased energy costs, reduced system capacity, voltage drops, and equipment overheating. Utilities often charge customers with low power factors a penalty fee to cover the additional costs associated with supplying reactive power. Maintaining a good power factor is essential for efficient energy utilization and reliable operation of electrical equipment. Power factor correction can lead to significant cost savings and improved system performance.